Recording is rolling. It is Thursday, January 9. Yeah, of course, yesterday I was at jury duty, set you guys up with some videos. So you guys tell me that worked out pretty good, which is great because learned something about torque and rotational inertia, which we're going into. Right. A few days back, I gave you guys these chapter 8 puzzles. We don't have a strict due date on those yet, but usually these topics last a couple of weeks. So I think the next about week and a half, we'll be able to make some time for those. You guys remember AP Classroom progress checks for units 5 and 6 have been open for a few days. The due dates to have for those are a couple of days after Martin Luther King Day because we have a 3-day weekend in the near future, right? Right. Not this coming weekend, but I think the next one. All right. So today, I want to show you guys a few notes on torque cross product, right? And then there's a lab page on your desk. Guys, here, guys, everybody focus here. Guys, look up here. Right. This lab page on your desk. A few labs, so we'll get to that. All right. So how about some civic stuff? I do have my jury summons, so I want to just show this to you guys just to see kind of what it looks like. Maybe your parents get these possibly. Yeah. So I got this in the mail, probably about a month ago. So I was supposed to show up at the course yesterday at 8 a.m. I was supposed to fill out a survey before I went. Let's see, where does it say that? It was supposed to go website, fill a survey. They want to know, are you American citizen? Are you a resident? Are there any disqualifying reasons? They want to know things like, would your employer pay for you to pay your paycheck while you're out of work? As far as I can tell, I think Brevard Schools does, right? But if they didn't, say if you had like a part-time job or something, then or a minimum wage job, they'll pay you $15 an hour, somewhere in here. So, there's this detail you can call the night before. Sometimes it's your service is canceled, they don't need you. That's happened in the past, but I call, they still need me. So, here are disqualifying reasons. So if you're not a citizen, you can't serve. If you're not a citizen of the county, if you're under prosecution for a crime or a convicted felon and your rights aren't restored. There are also a bunch of reasons. And so I went into this room. I was just waiting there for a few hours, but near the beginning, there was this list of reasons where you could leave if you wanted to. So if you're a law enforcement officer, because that could provide a conflict of interest. See if we can see this a little better. Expectant mother, so if you're like 7, 8 months pregnant, or if you just gave birth within the last few months. Extreme hardship if you're 70 years old or have an incapacity. So we go talk to the judge, and you might be dismissed for one of those reasons. Yeah, so it's got some other details here, but well, I don't know. Yeah, what ended up happening was as I was there was a plea deal taken right at the last minute. So yeah, so I was there for a few hours, but then ended up out of the evening, which happens sometimes too. I think usually like 90% of the time, something like that, these things end in plea deals. They never actually go to court. All right, so let's look at, you guys got your notes out? All right, let's do some notes here. Sure. All right, so here, I'm going to rewind a little bit. I was showing you some of these slides the other day. All right, so here you go. Maybe this is a good place to start. So inertia in a rotational sense. You guys remember those 2 meter sticks I passed around the other day? Okay. So still got them in this corner of the room. If you want to get your hands on this. So if you shake these back and forth, even though they have the same mass, same weight, same, right? If you just pick them up, right? If you shake them back and forth, say they're pivoting about the central point. One is more difficult than the other. In fact, this animation looks like the one on the right would be 9 times more difficult than the one on the left because it has 9 times the inertia in a rotational sense. So it's not just how much mass, it's where is that mass located. So you do mr squared and you sum it all up. Okay, that's for point masses. All right, then I showed you guys this table because there are some common type rigid body objects that could rotate, right? So like this basketball, you could split this up into a billion points and do the mr squared for every single individual point. But the aggregate effect, and you need calculus to show this, right, ends up being a factor of 2/3 for a basketball, or anything that's a spherical shell where all the mass is like on a sphere on the outside. And it's rotating about central axis. So if you spin it on your finger, then it has this much inertia, 2/3 mr squared. right? And then all these other objects, right? Now, you don't have to memorize this table, but you might be given this table or given a specific value, like, oh, there's a cylinder that's rolling downhill, so I equals 1/2 mr squared, and then you have to apply it, right? Okay, so of course we're going to get to that. Parallel axis theorem, AP just brought back in this year. They haven't been doing this the last few years, but they just did. So this is what if it's revolving around something that's not its own central axis? So you can start from this table, like this basketball here. So okay, it's 2/3 mr squared about its own central axis. And what about an axis that's parallel to that? Hence this parallel axis theorem. All you do is very simply is add the md squared around that axis it's revolving around. A really common application is with a ball rolling across the floor or down an incline. Eventually, you'll see down an incline. Okay, so it's not actually rotating about its own central axis. It's rotating about this point all the way down here, where it's touching the surface of the table, or of the floor. So you have to consider that mr squared, right? And it actually ends up being more inertia, it's like 5/3 mr squared. Okay, all right, you guys good? Okay. All right, show you guys torque. One of my classic examples is opening a door. This nut could be where the door hinges are. This point on the end of the handle could be like where the door handle is, right? If you're looking from above, okay? So R cross F. So you get this radial arm R, right, times how much force you're applying. But one more detail is this cross product. So you need the sine of this angle theta. You really need the perpendicular components. It's like if you're pushing parallel to the wrench arm or parallel to the door, it would never turn it, right? Never turn the wrench, never turn the door. Okay, and only the perpendicular component matters. Now be careful because sometimes, I don't know, AP question, textbook question, you might be given this other angle here. Guys, if you were given this angle, no, do you guys see where my mouse cursor is? Let's call that alpha. Okay, this would not be RF sine alpha. No, that wouldn't work. Guys, it would be, if you plane off alpha, it would be what? R times F times cosine alpha, right? So be careful about that. This angle theta that I have up here is the angle between the two vectors. Okay, but if you did from the perpendicular, then this would switch from sine to cosine. Okay. Sometimes you see a question framed that way, so be careful. Okay. Oh, and then if there's a net torque, suppose I have this applied torque here, and I subtract out maybe some frictional torque at the point of the nut. Okay? I get some net torque. That's going to cause an angular acceleration. This green box right here is Newton's second law of motion in a rotational sense. It looks a lot like F equals ma. It's analogous to that, but it's torque equals I times alpha. Okay. And so this wrench, if I go back a slide or a couple slides, I bet that wrench could be modeled pretty close to this one. You guys see this rod about an endpoint? Maybe if I measured the mass of the wrench and the length of the wrench, I could call it 1/3 m all squared. That'd be probably pretty close, right? And then if I knew the net torque, and then that would be where that I would go. Okay, is it? You can figure out how much it was accelerating in an angular sense. Okay. All right. Now this one here, I'm going to show a little bonus video for you guys. When we talk about torque in this class, I'm going to use AP's convention, which is talking about clockwise versus counterclockwise. Guys, this wrench is going to move which way? Clockwise or counterclockwise? Counterclockwise, right? Like opposite of a clock hand, counterclockwise, you said, right? If you said clockwise, you're actually correct if you're standing on the other side, like looking from behind the screen, wouldn't you? That actually would be clockwise, okay? So is it clockwise or counterclockwise? Well, it depends on your perspective. It depends where you're standing in the room, okay? So there is a mathematically better way to just describe like universally, so it doesn't matter where you're standing in the room, okay? Which is to use what's called this right hand rule. Now, this gets a little tricky because you think, okay, well, this rotation could be like on a 2D plane. What this right hand rule considers is, well, if say like I got my index finger and my middle finger in the directions of what that plane is actually rotating, your thumb will actually point in the z-axis along a third dimension, okay? And you can define torque along that third dimension. And as if it's its own vector, right? And then that can take care of that too. Okay. And that's actually where this matrix math pops up. Have you guys solved determinants like matrices? Have you guys seen this in a math class, maybe algebra 2? Here, show hands. How many guys have seen a matrix solved? Okay, a couple of guys. Okay. I ask this every year, and a lot of students have never seen this. I was asking some of my honors classes a couple days ago, and someone said they had seen it. Anyway, AP does not get into this math for this class, but if you go to college, you're going to see this. You could solve in 3 dimensions. Here's a 2-dimensional example up in the right, but here's a 3D example down here. I, J, and K are X, Y, and Z axes. Right? Sometimes you say I, J, and K instead of X, Y, and Z. Right? But what if you have like this crazy 3D type motion? You want to figure out exactly what does the torque look like, right? If you're an engineer, maybe you have to solve it in 3D so you can design a big old 3D structure, right? So I'm going to show you a video example real fast, just so you have exposure, so you've seen it at least once. You know where else I've seen matrices they show up all over the place in high level math and science classes. For my master's degree, I did economics, and in economics, maybe you have like a bunch of economic variables, like what's the unemployment rate, and what's the inflation rate, and what's the poverty rate, and what's the, you got like all these variables going on, and you try to figure out, well, how does this tease away from this in the data because it's a big old mess of data, and so they'll set up a big old matrix, and they might have like 10 different variables going on, right, to tease apart the data. So you have like a 10 by 10 matrix or something crazy. So let me bring in. See, there you go. I found one on a YouTube channel called Organic Chemistry Tutor. Okay, so I'll show you guys a little bit of this, skip through a little bit. Just kind of.
Say if vector A is 3 minus 5k
Yeah, thank you.
minus 7k, and vector B is 2 minus 3. So what is the cross product?
Let me see if I can get my
Vectors A
volume rerouted here. Got to switch some stuff.
What I like to do is this is I, J, K, which corresponds to the X, Y, and Z components of a vector.
Okay, so how this would apply to a cross product in physics is, oh, this A and B could be R and F. So A could represent like the radial size and orientation of the wrench. Think in 3D, like that crazy like 3D looking wrench turning nut. Okay, so 3I means it's think of it like a Cartesian coordinate. If you're going from the head of the wrench to like the end of the wrench, you got 3 units in the X direction, 5 units in the Y direction, and then -7 units in the Z direction. Okay, right? That's how the wrench is oriented, and also how long it is. Right? You can do a crazy Pythagorean theorem and figure out how long it is. Right? And this B could be the force, and that's how you're applying the force. So now you're coming on some weird angle. So you're pressing a force that's 2 units in the X direction, -6 in the Y, and 4 in the Z direction. Right? And we're gonna figure out how exactly does the wrench turn. Okay. Right, so we can set up a matrix.
Vector. And then first we need to put vector A in the middle because that comes first. So it's going to be 3, 5, and -7.
All right. So there's a specific. Yeah. Oh yeah. So all good here. All right. So there's a specific way you solve this. Again, I just want to show you guys just for exposure. But really the best way to do this is just to solve lots of these in a math class, do lots of practice. But again, AP is not going to quite ask you this. I see it's in college though. Right. So this is how you can solve a determinant. Again, it shows up in a lot of math and science, especially in higher level college classes. Right, so you want to do this. Right, but I'm going to kind of breeze through just so you guys can see exposure of how to solve this. All right. So like torque, we're doing R cross F. Here's R. Here's F. Right, and we're figuring out like what's the torque going to be. Right. So they actually solved it right at the 4-minute mark. Here it is. Right. So you guys see the C, and oh look, guys, what does this arrow above the C mean again? It means it's a what? Vector. There you go, because torque is also a vector, right? Has a direction associated with it. Right. So this right here, if that was like a single vector, you can interpret the turning motion being like plane perpendicular to that is what it would be. Okay. Now that's actually the answer. Like he could just stop this video right here and he solved it. Right. The rest of this, he says, well, how do I know? What if I made a mistake? Because it's easy to make a little mistake in math and then everything gets off. Okay? So you can take your answer and you can check. Because, guys, if you have two vectors that are truly perpendicular to each other, then how much of those are parallel in common? Nothing. Right? Nothing at all. Right? Like there's nothing parallel at all. Right? Kind of 4 times distant like work we did back in the days. Right? All right. So he said, well, how can you check parallel? And what he does is he takes his answer, which is this C vector right here in 3 dimensions, and you can take either A or B because this should be perpendicular to both of those, definitely by this point. Okay? And do what's called a dot product, which is a different kind of multiplication, which only, oops, there's his dot product right there. Right? And if it comes out to 0, then that would indicate that he probably did it correctly because so you can do A dot C or B dot C, and each of those should 0 out. Right? So no, dot product's a little easier math. Again, I'll leave it for you guys. But yeah, he did get 0 at the end. I guess he got 0. And the rest of the C, he tries the other one, he also gets 0. Okay. All right. So again, there's just a little exposure to cross products. Not going to show it AP exam, so I'll leave that to you guys to learn more about that. All right. So that's that could solve that right there. Okay. All right. We're turning that nut right there. All right. Also, we got, all right, this we're gonna save for another day. All right. Okay. Equilibrium. I think this is the last slide I showed you guys a couple days back. All right. So sort of picking up from here. All right. So last semester I told you guys equilibrium, all the forces zero out. That could be equilibrium. Right. Here's cheated edge, and okay, you can go along each axis, x-axis, y-axis. That'd be true. Right. Now in 3D, you have to consider 3D. Right. All right, now there's one more important condition for equilibrium, right, which is that torque we just talked about all day today also sums to zero. Right? And in 3D, you have to consider all these axes, but in 2D, really only have to consider the axis. Right? Because if you go into, for example, civil engineering, like this is slide one that's going to be the beginning of anything that you design. Right? So, right, this is your set of conditions, and then you can design anything from there and figure out exactly what's the stress in any little component that anything you build. Okay? All right. All right. So, here we go. All right, I have two slides that look pretty similar, and this is going to lead to the lab today. You guys see this materials on desk and lab paper? Okay, so we're going to bridge to this then. Oh, yeah, okay, so this worked out perfect. All right, so I got a Seesaw version and I got a scaffold version. First, I want you guys to see what the little subtle differences between these two. All right, we're going to just do the Seesaw half of this lab today. See, you guys see a Seesaw? Like there's a single point in the middle, right? Suppose you got two friends, right? Does it make sense maybe the light friend you have parked way out here and the heavy friend is closer to the pivot point? Like that could balance it out possibly, right? Okay. I'm about to show you guys the mapping of that. Okay. So the sum of torque goes to zero. Now, I'm going to start with this pivot point. I think this is probably the most intuitive way to do this. It's not the only way to do this, right? But I'm going to take this pivot point and say sum of the torque about that. Okay. So if I have 3x and then this mg pulling out this way is the force, there's my force dot distance this way. That's this one. Yeah, right here. Okay. Now that's, guys, which way is this one left pulling? Clockwise or counterclockwise? Counterclockwise. See, it wants to make the whole thing move counterclockwise. Okay. And this one on the right should balance it. Right? So I got 3 times the weight, but only 1/3 the distance. So if I cross product that, it's the same amount of torque, just the other way. Now that one's clockwise, isn't it? Right? That should zero out. Right. So if you either didn't know one of these weights, or if you knew the weights but you want to figure out where to put it, right? Those are puzzles that you could solve. Right? Is that? Okay. Here, Amanda, put your phone away. Look here, look here. 2%. Okay. All right. All right. So you guys get that? All right. Now your lab version of this, I'm just gonna have you guys hold the hold the spring scale right. Actually, ooh, that's what I need. You need to grab some spring scales. All right. Hold the spring scale right here. I'll model this for you guys. All right. And that'll be the pivot point. Now the tricky version of this, a little bit more involved versions. Technically, you don't have to pick this triangle point as the pivot point to sum the torque out. Technically, you can pick any point, and the torque will still zero out. Right. Now it gets a little trickier if you don't pick this point. Here's why. Notice I never considered the force that's from the pivot at that point. You see, I just ignored that because it's kind of like if you press on the door hinges of a door, that'll never turn the door, will it? Because it's R cross F, well, that R would be zero, that radial distance from that point itself. Okay? If you pick any other point, like say pick like this point right here, now I have to consider this force down and this force down, but also this upward force from the pivot point. Now it'll still zero out mathematically, but it's an extra force I have to consider. Okay, and I bet this force has to. Do you think that this force would have to carry both of these weights and maybe also the weight of the stick if you consider that too? Right. Right. So just balance those out. Right. So, but if you're ever like missing a force, like I don't have enough information, then if you pick a pivot point that's intuitive like this, then that's one less force to work with. Right. Which sometimes is the only way to solve it. Okay. All right. All right, let's look at the scaffold effect. No, okay, now this lab I think I want to save for tomorrow. It's on the other side of that paper. But this is a little bit different setup. Oh, look at this. Now I got two spring scales holding up. It's sort of like two pivot points, right? Right, and the classic question here is, suppose you're walking back and forth in some scaffolding. Actually, this was do you guys remember Paul Hewitt? Right, shows some of his videos sometimes. This is one of these questions that got him involved in physics. I think he was like, he was in his 20s working odd jobs. He was like painting signs. He was painting these billboards. And he was walking around taking it home. I wonder, as I walk closer to the right, closer to the left, what's happening to the tensions in these ropes? Right? Now, let's think about that. Guys, as you walk closer to the right, what do you think is happening to the tension on the right side? Increasing? You guys think? What's happening to the tension on the left side at the same time? Decreasing. You're right. Do you think those two tensions have to add up to the same value regardless, though? They do, because they have to hold up all this weight. But how did you solve this exactly? Now, this you could not solve last semester. I mean, you could do force equilibrium. You say force up equals force down. That's not quite enough information to figure out exactly what is the tension in each of these spring scales, each of these ropes. Right? because now you have to consider the location, like where are you walking back and forth on the scaffold, okay? Okay, and that's where you have to bring this torque. So I've got two boxes down here. I got my force equilibrium, that's one equation. I got beneath that, oh, is the torque also zeroes out, torque equilibrium, okay? And now there's enough information where in principle you can solve that, and that's gonna be tomorrow's lab, okay? You see that? All right, so let's go back to, let's start here. Just need to grab a screen because I want to demo this for you guys and then give you guys the rest of class to figure out this one. All right, so right, this is your basic setup right here. Right, you guys got these meter sticks on your desk. Right, this is oriented correctly. That's it. We're going to give you guys some spring scales so you can hold this up in the middle. Right, slide this around, kind of balance it out. Right, you guys also have some lab weights. Right, here, let's do one that I hope is kind of intuitive. I've got 1 kilogram here, and I got a half kilogram here. So let me show this on the camera so that it shows up in your video too. Right. So go back over here. There you go. Thank you. All right, so I have 1 kilogram versus a half kilogram. Okay, and I got this set up with the meter stick. Okay, it's going to balance at the 50 centimeter mark right there. Right. Okay, and I got these brads where I can hang these weights. Okay. Now, here, suppose I slide this one out. Here, just because it'll fit in the space, but we'll bring this out and show you guys a bigger version. Okay. Suppose I hang the 1 kilogram 10 centimeters away right here from this pivot point. I'm going to hold this up from this pivot point right in the middle. Okay. Where do you think the half kilogram should go to balance it out? Like 20 centimeters away on the other side? You guys think here? So here's a 10 centimeter arm with 1 kilogram. Right, so you can do, right, here's 20 centimeters. So it's like twice the distance from the pivot point, but only half the mass and therefore half the weight. Right? I think that should balance. Here. So this part, I don't think we'll fit quite on camera, but we bring this up here. Let's see how well that does. If I slide this, I put, oh yeah, that works right there. You see it balances? Kind of a tenuous balance, but it does balance, right? If I slide these back and forth, it should go all wacky out of balance. Okay. Right, let's see. Guys, I just slide this one to the left a little bit. So I don't want, sorry, to your guys' right. Which way is it going to go now? Now it's out of balance when I let it go. Clockwise or counterclockwise? Ooh. Yeah, see, it did go. See, from your perspective, is that clockwise, I think? Right? Is that? All right. So let's take a look at this lab page then. Right. So first of all, make sure that you are on the side where there's 1 spring scale holding up and 2 lab weights down. Right. Just to show you guys the side that you're not on. If you flip it over, I see 2 spring scales pulling up and only 1 weight down. So that's going to be tomorrow. Let's go back to the side, the seesaw side. Are you guys on the seesaw side? Right. All right. Now, the right half of this paper and left half of this paper can be the exact same setup. I just want you to do mathematically from 2 different perspectives. Okay. Do you guys see this detail right here? It says pivot point scale. You guys see pivot point scale right here? Is that right? So you'll sum the torque about the scale, right? Which I think is probably the most intuitive point anyway. Right. Now later on, do you guys see the left side of this page? Right. Now the left side of this page, you don't have to physically change anything. You can leave the spring scale and the weights exactly where they are, however they balance. Okay. The left side says pivot point 0 centimeter mark. So the only difference is you're just gonna pick like this really kind of random point right here and sum the torque about it and see if it still gives you the same answer. And I bet it does. Okay. Okay. So it goes here. Now the premise, because want to give you guys something to solve for here. I think it's a good way to do this. Okay, is let's say that one of these is a mystery weight. So out of these lab weights on your desk, go and pick a couple of lab weights. And I want you guys to make believe that you do know one, but you don't know the other. Like, I know this is 1 kilogram, so I'll call it 1 kilogram mass. Okay. But let's say I don't know what this is. Okay. Okay. You guys get that? And then at the very end, you're going to get some value that you calculate. And then I want to see how close it actually is. Okay. So if I got like a half a kilogram here at the end, it's like, oh, I nailed it exactly. Okay. You see that? All right. Actually, I put them in terms of weight here, not mass, but that's okay. Look at that. All right. So what does this look like in terms of torque? Right. So on the right side, if I do this from treating this is the pivot point right here, like here's my pivot point. Okay. I've got this weight on the left side causing a what kind of torque would this be? Clockwise or counterclockwise? Counterclockwise, right? So that's going counterclockwise there, right? And then again, from that reference point to the point, this one's pulling clockwise, right? Okay. And those two torques should be the same. Maybe call it torque left and torque right. Right? It should be the same value, well, equal and opposite so that they zero out, equilibrium. Okay. And what about the spring scale? Because the spring scale is applying a force at that also pivot point, but how much torque is that? Zero, because it has a distance of zero from itself. So zero distance. Okay. Right. Also, you maybe consider the meter stick has a little bit of weight, so there's a space for that too. Okay. All right. Show you guys how to interpret this here. All right. So we're going from this scale here. So you measure, all right, the weight on the left, or let's say the left weight you're allowed to know. So you put that there. So for example, if I have 1 kilogram, what number would I put in for, here, I'll do a model example. Don't copy this, but just get the idea. Okay. How much does this weigh in newtons? 10 newtons. So I do 10 newtons. Okay. Now my example I showed you guys that was 10 centimeters to the left. Oh, yeah. Do it, do it.
You change it to newtons in the lab.
Right. Yeah, it's gonna be in newtons. See, there's a unit here that says newtons. Right. Yeah, so these are gonna be forces. Yes, they record the weight value. Right. Now, notice the setup here. It says x left minus x scale. So x left minus x scale. So if the x scale was sitting at 50 centimeters and this was at 40 centimeters, 40 minus 50, that'd be like negative 10. Okay. Now I gave you guys the negative sign just to ensure that everybody for sure gets that. Okay. Again, don't copy this, but I just want to show you guys that this works. So it'd be like that. Right. You guys get that? I did 40 minus 50. Okay. All right. Questions so far? Okay. All right. So therefore, what's the torque? Oh, well, since I know that torque is equal to R cross F, right? And these are perpendicular because the radial arm is horizontal to the floor and the weight's pulling straight down, right? So I can just multiply them. Here's what's 10 times 10? 100. And I gave you guys a unit of Newton centimeters. And that one's in newtons and that one's in centimeters. Right. So that's all you need. Okay. Okay. Again, don't copy this down yet. I'll also throw in a negative sign because I remember this is just my example here. Okay. All right. The one in the middle. I said, well, the meter stick itself probably has some weight, so you have to consider that. Like, especially if this is off center. Like, I put this spring scale maybe at the 50 centimeter mark at the center mass, so it could just all cancel out. Right? But if you put this off center, then you definitely have to consider this. So it looks like the setup here. I said, just go ahead and put it right at the center, right? Just to make this one pretty straightforward. Okay. Now the weight of the meter stick. I measured that this morning. I got a mass of 120 grams. I measured a few of them. I got about that number. So that would be 1.2 newtons, right? But just like we've been saying today, if the center mass of the meter stick is aligned with your pivot point and you're measuring with torque with respect to that, the distance from itself would still be zero, so it would cause no rotation itself. Okay. So for this one, just go ahead and put the spring scale at the 50 centimeter mark. Right. Right. Now, the scale itself, you can read a force rating on the scale. Suppose here, I'm just gonna. All right, so here, if I read the scale, what does it say? Right, and it's kind of how this ends. Suppose you got like 16 newtons about something like that. Okay, and the fact that it's pulling up versus the weights are down, that's why. Ooh, do you guys see I also threw in a negative sign there? Right, I was really trying to help you guys out with the negative signs because these are vector values. So if the weights are pulling down and the spring scale is pulling up, I have to consider opposite direction. Okay, but it still causes no torque because you're measuring with the torque with respect to that point, kind of like the pivot point. Right, so we got that. So anyway, you add up all the torque. Now this one is going to zero out here. This one zeroes out here. So guys, what's the total torque in that whole system? Yeah, sorry. Yeah, I asked the wrong question. You're right. It should be zero. But so far, what I got is negative 100, right? Okay. So actually, just for this one, this number should be this number. And for me, for my numbers, again, don't write this down. This is just my model example. It'd be negative 100, and then the unit there is embedded as Newton centimeters. Okay. Okay. Now, since this torque has to sum to zero, and I wrote that right here. I wrote sum of torque is equal to 0 Newton centimeters. Okay. Therefore, you can know the unknown torque that we haven't talked about yet, which had for my model numbers has to be how much? Yeah, positive 100, right? So I got positive 100 on the left, on the right side, because it says right there, torque on the right side. You guys can see that better on the paper in front of you, right? Okay. Right. Because these two boxes have to zero out. Okay. Is there any questions so far? Okay. So okay. Right. All right. And since I know where I put it, notice it says X right minus X scale. So I'm looking for this gap right here. And I was showing you guys mine was at the 70 mark minus 50. You guys, what 70 minus 50? 20. So let's go 20 centimeters right there. That's like the radial arm. Okay. And then torque equals R cross F. So if I know torque and I know R radius, I can solve for F. And that would be, let's see, divide that. Is that like 5 newtons? Right? Oh, and that's exactly what this was. This is a 5 Newton weight, isn't it? Okay. Right. Okay. Now, here I want to demo this other one for you guys. Right. If you just leave the system the same, you don't have to change anything. You just very simply change the pivot point to this point right over here. Okay. Now it's a little trickier mathematically, but if this was like the door hinge, and it really is just a random point, okay, this is causing, looks like clockwise torque. The weight of the meter stick itself is causing a little bit clockwise. The spring scale pulls back hugely counterclockwise. Okay. And then this weight on the right side also gives a large clockwise torque. Okay. So I just drew 4 torque values. Right. This weight, the meter stick weight, the weight on the right side, and then the spring scale pulls back counterclockwise. Okay. Because what do those 4 torques have to sum to? Still 0 mathematically. This one's a little trickier conceptually, but still 0, okay? Which is still here. So it's a little bit different process, but if you follow this, I bet you still get the correct reading for this mystery weight on the right side, right? You guys think you can do that in the last 15 minutes here? Right? All right. So all I need you to do is get you guys some spring scales. I'm going to close down this recording here. And then, guys, hold on to that lab page at the end today because we're going to save the one in the back for tomorrow.